So, to go over equilibrium reactions, we first want to break it down into parts. If we kind of use the A and B reactant and product from the Pogel packet, forward reaction is where reactants turn into products. So this is what we should already know. Before today, your world of chemical reactions was you start with reactants, they make products, and then we're done. We're done when we run out of reactants. One of the things that you're going to notice when we get more into equilibrium reactions and stop using like letters A and B to represent reactants and products, and we actually give you chemical formulas, you could still think of an equilibrium reaction as a single displacement if it started with an element in a compound making a new element in a compound. Or it might be one that's a double type displacement. I mean, one direction is synthesis, the other direction is decomposition. So you'll still be able to recognize a lot of this when we start getting rid of the generic A and B format of it. But if we take it step at a time, it's easiest to just give you, here is in general what it would look like. My next slide, we could call this either the backward or reverse reaction. So what we haven't been aware of until today, possibly, is that products can turn back into reactants sometimes. Now, I'm not going to say every chemical reaction can have this happen necessarily, but equilibrium reactions can fairly easily have this occur. So we could show that one of two ways. I could either show B becoming A as product, arrow to the left, making A, or quite frankly, I could just flip the entire equation around to show the reverse reaction.
How do you determine then what's the product and what's the reactant?
So what we will do, instead of flipping the equation like I do from the first to the second example, we'll always keep reactants on the left side of the arrow, products on the right side of the arrow. I think the point I'm trying to make with the second B making A example is that, like you said, it'd be hard to determine reactants or products, so we can't do it that way. Instead, we have to use a double arrow, which is what I'm showing on this slide then, that A makes B while B makes A. So your number one way to identify, is this a reversible or equilibrium reaction, is that double arrow between things. So even if we only start with part B, like in the Pogel packet, page 1 says, well, what if you start with 100 parts of B? B is still considered a product because it's on the right side of the equation. Reactants are on the left side of the equation. So for identification purposes and vocabulary, that holds true. It's just that sometimes you have more reactants or sometimes you have more products. So in a reversible reaction or an equilibrium reaction, the forward and the backward reactions are occurring at the same time. A is making B, B is making A. more slide to go. The good news is for you that that math that you did in that Poggle packet, you'll never have to do on an assessment of ours. So that page 2 where you had to figure out how much is lost and how much is gained, we simply want you to try that once to see what's happening. Next class, we'll be doing an activity to show that as well, but that math you are not responsible for. So, a normal reaction is done when you run out of reactant. Everything gets used up. Hopefully that's kind of straightforward to you in thinking. If I poured some hexane on a lab bench and I lit it on fire, once all that hexane's gone, the reaction stops. Equilibrium reactions don't work that way. Instead, reactants make products, products make reactants. An equilibrium reaction is done when we've reached equilibrium. And we reach equilibrium when the amount of reactant and product stays the same. It doesn't mean that I have a 50-50 split of the two. The Poggle packet should have showed you that. You don't necessarily have a 50-50 split of the two. It just means that the amount of A I have now stays constant. Jeb?
Is that due to like ratio between the two?
Yeah. So that ratio stuff on the math, the Poggle packet, is where that's derived from. Again, another reason why we want you to see the math, but not necessarily do the math an awful lot. The third bullet point in this slide, when you reach equilibrium, that does not mean that things have stopped reacting. What it means, as my fourth bullet point says, is the rate of the forward reaction balances with the rate of the backwards reaction. So products are being made at the same rate that reactants are being made. I know this is a little bit wordy, so I'll give you a little time with this, but my very last point then is that the reaction has not stopped. An equilibrium reaction will never stop. As long as reactants bounce into each other, they can make products. As long as products bounce into each other, they can make reactants. And it'll go on and on and on. I like to use an analogy to explain this equilibrium, and that would involve us taking a field trip. Lindsay, you ready to take a field trip? All right. The first time I ever flew on a plane was when I was, I think 22. And I flew to the smallest island of Hawaii called Kauai for a cousin's wedding. And it was awesome. Hawaii weather is far superior to Wisconsin weather. I mean, today's a nice day, don't get me wrong. But every morning in Hawaii starts off in the 60s and the 70s, and you have this little mist in the air because of the humidity. And then it just, is nice 85 every single day. There was this beach that we would go to that was near our hotel. It actually had lava rock in the water. I mean, I'm not a strong swimmer, so it was nice that there was these rocks that were kind of surrounding the beach area, so then you wouldn't get pulled in by the tide. Every day when you're at the beach, there are people in two different locations. They're on the sand part, or they're in the water. Now, if you're on the sand, laying out there working on your tan, right, Gretchen? If you get a little too warm from that hot Hawaiian sun shining down on you, where might you go, Gretchen, from the sand area? Into the water. Sure, why not? You go into the water after a while. If you're in the water, after a while, you're in the water too long, your fingers start to get shriveled up. Again, waves splashing on you. Maybe you're tasting too much salt that's flying into you. Well, if you're in the water and you want to get out, you go back into the sand. Two things are working independently of one another. People from the beach are going into the water. People from the water are going into the beach. And there's this constant back and forth that's occurring. Now, if all of a sudden a busload of people show up and they're all on the beach gets pretty crowded. There's a greater likelihood that people from the beach are going to start to go into the water. But if the water gets too crowded, now people are going to go back there as well. At some point, a balance is reached. It doesn't necessarily mean a 50-50 balance between people in the water and people in the beach, but there's going to be a balance that's reached between the occupants of that area. Some in the water, some on the sand. And every now and then, one person might stroll back into the water, one person might stroll back onto the sand. But it's not like, okay, you're in the water, you have to stay there for the next hour. Or you're on the beach, that's where you have to be. There's a constant flow back and forth. And eventually there's a balance that's reached at that beach site. Because there's a certain amount of towels laying on the ground with people laying on, there's a certain amount of people frolicking about in the water. Because that's what you do in Hawaii in the water, you frolic. Because Hawaii is a very joyous place to be. When I think of an equilibrium reaction, I think of balance. Balance doesn't have to be a 50-50 split. It just has to be when the amount of reactant in the product now doesn't change. If you were able to work on that Pogel packet enough with the graphing part of it, it's when the two lines are now parallel to one another. What we're going to be doing these next couple of days is studying that equilibrium reaction more. That forward reaction is making products at the same rate that the backwards reaction is making reactants. Then we have to get into, which a couple people got to, the very last question of that Pogel packet, of how can we shift equilibrium? How can we make things no longer balanced? And a couple of people that got to it, they mentioned temperatures one way. Well, if all of a sudden that 85-degree day turned into a 110-degree day, where's a lot more people going to be going? Into the water, because it's getting a little too hot out for them. So that could shift our balance. If I had 3 truckloads of third graders show up and they're all frolicking in the water, I don't want to be in the water anymore around all those third graders. I have 1 third grader in my household, that's enough. I don't need 60 of them to be around. So there's ways that we can shift that balance that we'll also get into. But that's it for this unit. We have to go over what is this type of reaction, equilibrium, forward making product, reverse making reactant, and a balance is reached. And next week then, we go into how do we shift that balance.